Hello all of you. Welcome to the fourth week of lectures on the course on analysis and modeling in chemical engineering. In this week, we will talk about modeling and simulations of chemical reactors. We will begin with recapping some of the ideas that you have learned in the undergrad courses in chemical reaction engineering regarding the mole balances and energy balances, and then I will apply it on certain classes of modeling problems just to emphasize different modeling algorithms that is used in chemical reactors. So, just to recap what we have so far covered in the course, we started with discussing how we use modeling in chemical engineering and what exactly is chemical engineering in the first place. Then we discussed the fundamental laws and concepts in chemical engineering, which we are going to use in different applications as we see in the course. And then in the previous week, we discussed about representations of processes and so on. So, when we talk about chemical reactors, I mean that is, you can imagine it as being the heart of a chemical plant. That is where the chemical reactions do take place, right. And when I talked about the difference between chemistry and chemical engineering, I have emphasized that how it is a problem of scale. When we are doing something in the lab, then we are working in a small scale, and the idea is more to discover, explore and synthesize new kinds of compounds. But when we are doing the same thing in a chemical plant, we already start with a known chemistry that is well established. But the goal here is to make the process faster, cheaper and safer, right. So, apart from the notion of a higher scale, we also have the motivation to make it faster and cheaper and safer and so on, right. So, when we look at chemical reactors, we typically begin with the idea of ideal reactors. In some sense, just like in thermodynamics, we talk about ideal gas, in chemical reaction engineering, we talk about ideal reactors. And the examples are the continuous stirred tank reactor CSTR or the plug flow reactor PFR. And accordingly, we have the solid gas reactors like packed bed reactor, and we have like a fluidized bed reactor and so on, right. So, all of these are modeled as ideal reactors. When we look at the reactors in the real world, they are almost always non-ideal. What this means is that whatever reactor models that we are developing in reaction engineering can only be an approximation of the actual reactors. And in general, what is happening is the reactors can either be close to, let us say, a CSTR or a PFR or the corresponding version in the bed reactors. And we try to use our analysis to first develop ideal reactors, and then we talk about how it can explain non-ideal behavior and how we can extend the same models to basically explain non-ideal reactors. For example, tank in series reactor is used to represent the behavior in between a CSTR and a PFR. So, the starting point in chemical reactors is of course this homogeneous reactors, and more or less these are the categories which are available for homogeneous reactor. We have batch reactor. In a batch reactor, you begin with some reactants in the vessel and we are mixing it and the reaction is taking place. By definition, it is always unsteady state because there is no supply of the reactant and the going out of the product. When the reactor is running, the concentration builds over time and we can stop whenever we want to stop the reaction, whenever we have achieved the required conversion, right. You can imagine that the batch reactor is naturally more convenient when we are dealing with small production capacities. But when we are going for higher production capacities, then we have to go for continuous reactors. So, in continuous reactors, we have essentially two ideal categories. One is the CSTR, as I said, continuous stirred tank reactor, and the other is the plug flow reactor, that is given right here, right. In both these cases, you have an inflow of the reactants and outflow of the product and the unreacted reactants, right. In almost all these cases, we typically assume that we have kind of a perfect mixing. However, in the case of a CSTR, the perfect mixing exists all over the vessel. That means the concentration inside the vessel, inside the tank, is the same as the concentration that is exiting from the vessel, right. So, C out is the concentration going out, and the same concentration do exist inside the tank, right. And now the CSTR can very well operate on steady state condition. When it is in steady state, then the concentration remains constant inside the reactor and going out. On the other hand, when it is unsteady state, then the concentration can change over time, right. But typically, you can imagine in a continuous process, we plan to achieve or we aspire to achieve steady state conditions, because that gives me a fixed conversion with time. There is no time dependence in the conversion or the concentrations going out. In the plug flow reactor, there is mixing, however, only in the radial direction, and there is no mixing in the axial direction, that is along the length of the reactor. And because of that, the concentration can vary along the length of the reactor, but the concentration is not dependent on time again if it is running in steady state operation. The concentration is changing along the length or along the volume of the reactor as we go from, in this case, left to right, but the final product, whatever is coming out, is having a concentration that can be independent of time when it is running in the steady state operation. In the case of a semi-batch reactor, it is in between these two extremes, where either the feed or the product is coming continuously. In this case, the feed is coming in, and in the second case shown here, the product is going out continuously, and the other stream, in the first case the product stream is not there, and in the second case the feed stream is not there. So, it is partly batch, partly continuous, and that is why we call it a semi batch reactor. And again, it is going to be always in unsteady state conditions, because there is not constant inflow and outflow, there is either inflow or outflow. Okay. So, to begin with designing these reactors, the very first idea that we always use is to use the mole balance on these reactors. And the mole balance can be performed irrespective of the geometry for any shape of the reactor in the following way. We can imagine that there is inflow of the different species, and I am referring as some molar flow rate, moles per unit time of species J. If there are multiple species, there are going to be multiple flow rate, and there is an outflow of this. In fact, the same model can be used for also the batch and semi batch, but in those cases, in the case of batch, both the flow rates are going to be 0, and in the case of semi batch, at least one of them is going to be 0. So, now this is in between, we have this reactor volume that can be any arbitrary shape, which has some volume V and some number of moles or molecules of species J. And finally, inside the reactor, depending on whether it is perfectly mixed or not, you may either have a constant concentration or uniform concentration if it is well mixed, or you can have a non-uniform concentration if it is not well mixed. If it is non-uniform, then the concentrations are going to vary inside the reactor, and therefore, the rates, which are a function of concentrations, are also going to vary along the reactor. So, in general, we can define a rate at a particular point as something like a control volume drawn around that point, the rate in that control volume. We can imagine if the control volume is very small, then the concentration within the control volume is like constant or uniform, and in that condition, we can basically express the rate at this particular point or this particular control volume as a function of concentration. Okay. So, now we can write a general mole balance equation that applies to all kinds of homogeneous reactor in the following way. We have basically the standard material balance equation, in minus out plus generation is equal to accumulation, and the in is my molar flow rate coming in, that is Fj naught for species J. The outflow rate is the molar flow rate going out, that is Fj. The generation in general is the integral of this Rj over this entire volume of the reactor. If it is perfectly mixed, we can drop the integration and say it is simply Rj multiplied by V, but in general it is an integral of Rj dV. And on the right hand side, we have accumulation, that is how the number of moles of the species J is going to increase with time, right. Typically, we can use the same notation for the number of molecules and the number of moles in this case, but I will be referring mostly in terms of number of moles of species J. That is what is typically used in the literature. So, now I will apply this particular mole balance, the general mole balance, for different kinds of reactors, and there are going to be simplifications depending on what reactor we are looking at. So, let us begin with a batch reactor, and in a batch reactor you have certain number of moles of species J at a particular time t. It is by definition in unsteady state, and there is a volume V of the reactor. For the gas phase reaction, it is the volume of the entire tank, but for the liquid phase reaction, it can be the volume over which the liquid is located, or the liquid volume in the reactor, right. So, now since there is no inflow and outflow in the case of a batch reactor, Fj naught is 0, Fj is equal to 0, and now we are left with only generation term, integral of Rj dV is equal to dNj by dt. And now, if I assume that it is perfectly mixed, which is generally assumed, then I can assume that the Rj is uniform across the batch reactor over the volume of batch reactor. And in that case, I can drop the integration and I can simply write this term as Rj multiplied by V, and then we will have the simplified expression for the batch reactor. Now, we can make some further approximations. For example, I can assume that the volume of the reactor is constant, or in the case of liquid phase reaction, the volume of liquid is constant. For the gas phase, it is typically not the issue, because gas will occupy the entire reactor volume anyway, unless you have a piston like arrangement that can change the volume with pressure and all that. In a normal case, when there is no piston like arrangement, if the vessel is rigid, then in that case volume is constant and the gas fills the entire reactor. In the case of liquid phase, of course, there can be a volume change on reaction, but typically the volume changes are fairly small, so that can be neglected. And in that case, again, we can assume that the batch reactor is operating at constant volume. And in both these cases, using the fact that the concentration Cj is defined as the number of moles of J by the volume, we can basically plug it in this equation and note that the volume is constant. So, therefore, we can basically get Rj is equal to dCj by dt. On the other hand, if the volume is variable, in the case of gas phase reaction, this means that you have some kind of a piston like arrangement where the piston can go up and down, changing the volume. In that case, the volume will change. And for the liquid case, if for example, there is a significant volume change in the reaction, then in that case, we want to account for that. And in those cases, again I can use the fact that J is equal to Cj into V, but now if I plug it in this equation, what you are going to have is something like d by dt of Cj into V, and now the volume is no longer constant. So, therefore, we have now two terms here. The first term is dCj by dt and second term is Cj by V dV by dt, that corresponds to basically the volume change taking place in the reactor. I can also write this equation in a different way. So, what I have just shown you can be considered as differential form of the equation. We will refer them as design equations. This is the equation that pretty much defines the conversion inside a reactor. But we can also write in an integral form, that is found by basically integrating this particular expression, and now I can get basically an expression of time that is something like this. We are integrating this from number of moles J to number of moles Nj naught dNj by minus Rjv, and you can see where it comes from. So, basically what I am doing is I am moving this on the left hand side, and we have dt is equal to 1 by V into Rj, and then we have dNj, and we are integrating from Nj naught to Nj, and this goes from 0 to t. But in this case, you see the limits are defined in an opposite manner, and therefore, I have plugged in a minus sign there, right. The reason I am doing that is because for the reactants, the Nj naught is bigger than Nj, and therefore, as a matter of convention, I basically integrate from Nj to Nj naught as opposed to Nj naught to Nj, because Nj naught is a bigger number for the reactants. So, this is what we can do for the batch reactor. Let us see how the same equation of general mole balance can be used for a CSTR. So, for the case of a CSTR, I again begin with the same equation, and I can again imagine that we have perfect mixing. That is the whole idea of continuous stirred tank reactor. When I say continuous stirred, it means perfect mixing, and in that case again I can replace this integral by simply Rj into V, and everything else remains the same. But now, unlike the batch reactor, we can also imagine that we have a steady state, and assuming that we have a steady state, the right hand side goes to 0, and now we can simplify this and get the equation for the volume, right. And again, since we know that the moles per unit time can be represented in terms of concentration, basically moles per unit time can be written as moles by volume into volume by time. What this means is that I can write my Fj naught as the moles per unit volume, that is the concentration, Cj naught into the volume per unit time, that is the volumetric flow rate. Let me call this some V naught, and similarly I can do it for the outlet. Fj is equal to Cj into V, and I get this particular equation. In most cases, you will see that V naught is equal to V, that is typically assumed. Again, for the liquid phase, it is typically the case because the liquid, there is not much change in the density. In the case of gases, provided that the inlet conditions, the temperatures or whatever is not very different from the outlet, we can again assume that we have V naught is equal to V, but we have to keep in mind that it is not generally true. We need to ensure that this particular condition is being met. Otherwise, we will go with this particular design equation. Now, let us now finally use it on the plug flow reactor PFR. In the plug flow reactor, as I said earlier, there is going to be a change in the concentration along the length of the reactor, and therefore, instead of applying the mole balance on the entire reactor, what we do instead is we apply the mole balance on an elemental volume between volume V to volume V plus delta V. And within that volume, again I can imagine that the concentration is constant, let me call it some Cj, and now we can define the incoming molar flow rate of species J from the left at V and outgoing Fj at V plus delta V, and then we have some reaction happening there. So, if I write the mole balance for this particular elemental volume or infinitesimal volume, we can imagine that the rate Rj is uniform within delta V, because we can assume that within that infinitesimal volume the concentration is constant, and then we have again inflow minus outflow plus generation is equal to my accumulation, and again if I assume steady state, the right hand side goes to 0. And now I can apply standard calculus, I can divide by delta V and take the limit delta V going to 0, and then we get a nice differential form for the mole balance. And just like what I did for the batch reactor, I can again integrate that, and if I integrate that, then I am going to get an expression for the volume as opposed to time for the batch reactor. Now we have the volume for the PFR, right. Keep in mind that since volume is used as a variable when I did the mole balance, we define the total volume here as some V1, right. Typically what we are doing is the concentration is changing along the length. So, we define the concentration as a function of V along the length of the reactor, unlike the case of a CSTR where the concentration inside the CSTR was uniform. In this case it is changing, and therefore, it is dependent on this variable V. So, for the total PFR volume, in this case I am using, just to not make it ambiguous, a volume of V1, right. But many a times this convention is not used, and this kind of an equation is also written as V, but just have a look whether it is referring to the variable V along the length or the total PFR volume, right. So, in this case V1 is the total PFR volume. Okay. Now, we can go ahead and apply something similar for heterogeneous reactors. There are mainly two classes of heterogeneous reactors which are commonly used. By heterogeneous, I means that there is not a single phase, gas or liquid. We can have basically two phases, let us say gas and solid. It can also be, and that is more common, is the solid is my catalyst, that is catalyzing the reaction, and the gas is what is basically flowing in. And in that case, unlike the volume, what is more important to us is the weight of the catalyst, right. So, in the case of like CSTR or PFR, we work with rates which are defined as something like moles per unit volume per unit time. But now, instead of volume, we want to use the basis as the weight of catalyst. So, we use these rates are a prime, that is something like moles per unit weight of catalyst into time. And accordingly, we will replace the volume V with the weight W, right. And then I have basically dFj by dW. We can also do it for 1, but let me keep it W because W is a variable, right. That is my differential form, very similar to what we had for the PFR. I only replaced V with W, volume with the weight of catalyst, and I replace the rate which was defined earlier as moles per unit volume per unit time by moles per unit weight of catalyst per unit time. And again I can have an integral form where the only change again we did is replaced V1 with W1. Let me show you the expression we had there. So, I am replacing V1 by W1 and Rj with Rj prime, and then we get the expression that is kind of shown here, right. So, this is what is we do for the packed bed reactor, that is considered more like a PFR. The concentration is changing along the length of the reactor. There is also something called a fluidized bed reactor, which is FBR, and in this case what is happening is the catalyst particles or solid particles, they are kind of in a fluidized state. What this means is that there is kind of movement of this catalyst pellets more like gas molecules. They are pretty much moving inside this. In the packed bed reactor, the catalyst particles are fixed at their position, but in the fluidized bed, the catalyst particles can freely move because they are in the condition of fluidization, right. So, in that case, we can imagine just like CSTR that the concentration inside the reactor is uniform, and therefore, these reactors FBRs are modeled as a CSTR, and again we are going to replace volume with the weight. For the CSTR, we referred them as simply V and W. So, let me keep it that way, right. And again I can get an expression for the weight of catalyst as something similar to whatever we had for the CSTR, but now I am going to replace this V with W and this Rj with Rj prime, and we get the equation for fluidized bed reactors. So, what you have seen is the just general idea of material balance, in this case mole balance, can be used to basically develop the design equations for all kinds of homogeneous and heterogeneous reactors. So, going forward, this is kind of the summary of what we have obtained. For the batch reactor, we assume perfect mixing generally, and in that case we can get a differential form of the design equation as the following, and the integral form as the following, which gives me the time required to basically go from Nj naught to Nj of the number of moles of species J. For the CSTR, we typically assume perfect mixing, that is by definition a CSTR, and we typically also assume a steady state. In that case, there is no accumulation, and in that case we have a simple algebraic form of the design equation. Then we have plug flow reactor, where we assume a condition of plug flow. There is a variation only in the axial direction. In the radial direction, we assume mixing, and again we typically assume steady state, and in that case again we have differential form like this and an integral form for the entire PFR volume as the following. And now we can do it for the packed bed reactor, which is modeled as the plug flow reactor, but we simply replace V with W in there, and for the integral form we simply replace V1 by W1. And then for the fluidized bed reactor, this is modeled as a CSTR. So we assume that we have perfect mixing and again steady state, and now I basically change the equation of CSTR by simply replacing V with W and Rj with Rj prime. So we are going to basically use the design equations further in the next class, where I will introduce the language of conversions and I will tell you how we can basically express the same design equations in terms of conversion, right? So with that, I want to conclude this current class. Thank you so much.